Yes? Okay, wonderful. All right. I'm going to close this question in 5, 4, 3, 2, and 1. All right. Now, there's a certain take home message from this question. Okay, that is appreciating that these are tetrahedral molecules, which are 3D molecules on a 2D plane. Now, if you try to consider them as 2D molecules, you're going to get this question wrong. Okay, let me show you what I mean by looking at your answers. Okay, you see that most people selected options A and E, but C is the second most popular answer, which is not correct. Okay, now why isn't C correct? Does anybody know? Why is C a polar molecule? It's not. So C is not a non-polar molecule. It is a polar molecule. Why? Anybody? Yes. What's your name, sir?
My name is Garrett.
Eric?
Garrett.
Garrett.
Yeah.
Garrett, go ahead.
So the reason why I think C is wrong is I imagine in a 3D space and it wouldn't match the same symmetry that A and E would in a 3D space. I couldn't tell you like if it's bent or anything, but I just know in a 3D space.
Yeah, I mean it's tetrahedral. It's not bent. It's tetrahedral. But you are right. I mean, the charges are not symmetrically distributed. Can we say? Do you see that in C the charges are not symmetrically distributed? You see it? I don't believe it. Give me a second, okay? So I got this. I don't know whether you can say it. I'm going to try anyway, okay? Right. See if this works. There you go. All right. So do you see this? So this is what we're looking at. So imagine my green atoms as the fluorine atoms, okay? And then we have the two bromine, which is everybody knows that bromine is orange. Nobody knows. I didn't know. Yeah, I was anyway, the idea is this, okay? So as it is drawn, it seems like what we have in the question, right? However, you need to appreciate that this is not a 2D molecule, it is a 3D molecule. Now, what we have is something like this. So you have two fluorine atoms facing this way, meaning you have a dipole moment from the fluorine atoms going in this direction. I need a better background. Anyway, okay, the dipole moment from the fluorine goes this way. On the other hand, my two bromine atoms are in a perpendicular plane to that, going in the opposite direction. So if we have a dipole moment going in this direction and this direction, because my fluorine has a greater dipole moment because of the greater electronegative difference, there will be a net dipole moment going in the direction of the fluorine atom this way. So as a result of that, this molecule will have a net dipole moment going towards the fluorine atoms in between the fluorine atoms in the okay, so this is why it is important for us to see the tetrahedral molecule in a 3D space. Okay, because if we try to see this in a flat world, it's not gonna fly. Okay? It's not gonna work for us. Okay, so now I'm gonna pass this around in case somebody wants to say this. I'll leave you to start. Okay, pass this around and then see. I mean, whether you can make sense with that. But do we have any questions, concerns, comments at this point? The idea is these are 3D molecules. You need to see them in 3D, not in 2D. Otherwise, I mean, things are not going to go in our favor. Now, keep in mind, if we have a tetrahedral molecule, if we can remember this or make a good note of this, is really going to be helpful. If you have a tetrahedral molecule with 4 atoms, the same 4 atoms bonded to the carbon atom or something like carbon, like silicon or something like that, then it's going to be a non-polar molecule. I mentioned the other day, as soon as you replace one of those atoms with anything else, it's going to become a polar molecule. Okay, if you replace one of those atoms with another atom, or maybe 2 of them with another atom, or 3 of them, then it's going to be a polar molecule. That's why the B, C, and D molecules are polar molecules, because there will be a net dipole moment. On the other hand, A and E, where you have like a perfect tetrahedral molecules, they are going to be non-polar molecules. All right. What questions, concerns, comments do we have at this moment? Anything? Any questions, concerns, comments? Okay. I'll reopen the question. I just want to point that out because that is one of the common confusions. Oh, Nathan, you also pointed this out. Yeah. This is one of the common confusions students have about tetrahedral molecules. All right. So with that, I just want to mention this as the last thing I mentioned in Unit 2, Module 4 before I move on to Unit 3, Module 1. So if you see molecules like these on the screen, which is composed of only carbon and hydrogen, they are known as hydrocarbon molecules. And then these molecules are non-polar, even though they have polar bonds. Carbon-hydrogen bond is slightly polar. Okay, even though they have polar bonds, they are considered as non-polar molecules for all intents and purposes. Okay, for all government purposes, these are non-polar molecules. Keep that in mind. Please make a note. It's really important. Okay, if your molecule only consists of hydrogen and carbon, like these guys, they are considered as non-polar molecules. That's it. Okay. So now that do we have any questions, concerns, comments before we do something else? All right. So let's try this. I'm going to actually start this to save a little bit of time. Okay. I'll give you a minute to think about this. Think about this chemical formula. C2, H2, F2. Okay. How many Lewis structures can you draw for this? Can you give it a shot? I'll give you a minute. Just a minute. Can you draw the Lewis structures for this? I'll give you a hint. There's a carbon-carbon double bond. Otherwise, you need to figure that out, right? There's a carbon-carbon double bond in there. But even without that hint, you should be able to figure out there should be a carbon-carbon double bond. Otherwise, it's not going to work. So here's what we have. Okay. There are three possibilities. So we can draw something like this. We can have the two fluorine atoms bonded like this on the same side, and the hydrogens on the other side. Okay. Or you can have the two fluorine atoms on either side, like one up and one going down. That would be two. Or you can have the two fluorine atoms bonded to the same carbon atom. That would be the third structure. Okay. These would be the only possibilities for this chemical formula. Okay. By the way, these structures are not considered as resonance structures. Can somebody tell me why these are not resonance structures? Okay. Anybody? Does anybody know? Laila? Take the microphone, Laila.
Is it because the bonds stay the same?
Yeah, double bond is not changing, right? The bonds are the same. Exactly right. Yeah. So in resonance structures, the placement of the double bond changed. But in this case, the placement of the double bond is not what is changing. What is changing is the arrangement of the atoms in the space. Okay, they have different arrangements. Therefore, these are known as isomers. Okay, these are known as isomers. There are three isomers possible for this chemical formula. So let me write that word isomers so that we are kind of familiar with this. Isomers. And then we kind of heard about this too, right? When you have these main groups on the same side, just like in this guy, right? In this isomer, you have the two fluorines on the same side. And those isomers are known as cis isomers. On the other hand, if the main groups are on either side, they are known as trans isomers. And there's a name for this as well. I don't know. I mean, I can't remember now. But anyway, so I want to point out at least cis and trans. The reason is, I mean, you might have heard about this, right? When you go to Costco somewhere, right? You have like butter or margarine or whatever with cis fatty acids or trans fatty acids. So when you say cis and trans, this is what they mean. They have double bonds. If they are trans, they have the things going on either direction, on opposite directions. If they are cis, then you have the things going on the same direction. That's the idea there. Okay. So when you have cis, they have like things in the fatty acid chain that's going to affect the packing of the fatty acid chains. Therefore, it's going to decrease the melting points and stuff like that. But it's for another discussion. I mean, we'll talk about that later. All right. Anyway, so that is not the point of this discussion, right? So we want to know which one of these isomers are polar. So let's think about that. By the way, I would like to convert this to line structures. The reason is they are much easier to draw. For example, I can draw the cis like this very easily. So here's my cis isomer, fluorine. I made it upside down. Okay. And here's my trans isomer, fluorine. And then here's my other isomer. They're much easier and faster to draw. So I mean, therefore, I prefer line structures when I have to deal with carbon-containing compounds. All right. So anyway, my question for you is, can you let me know which one of these isomers are polar? Go ahead. Do it on our whiteboards. Which one of these isomers are polar? There are two polar isomers here. Which ones are the polar isomers?
That's why we see.
All right. I want to talk with somebody. Any volunteers? Nobody wants to talk with me? No. All right. Anybody? Okay. All right. Leo, can I talk with you, please? Can I talk with you?
Oh, sure.
Thank you. Hey, Peyton, do you have a microphone on you? Thank you so much. Leo, my question is, I want to figure out which one of these isomers are polar. Okay. What do you think? The first one, is it polar or non-polar? Let's do the bond dipole moments with me. Okay. So I'll do it with you. So we have carbon fluorine bond. Here's the bond dipole moment for that. Here's another one. Here's the bond dipole moment for that. Here's the hydrogen carbon bond. We have a very small negligible dipole moment going towards the carbon because carbon is more negative, like this. Right? So these are my bond dipole moments. Looking at the bond dipole moments, I see that all the heads of the bond dipole moments are pointing in the same direction. So what do you think? Is there a net dipole moment?
No.
So now all of them are heading to the same direction, right? Do you see that? Okay, all of them are heading towards the fluorine. Right? Therefore, is there a net dipole moment in this molecule?
Yes.
Yeah, so they are going towards fluorines like that. So here's a net dipole moment of this molecule. Yeah. So if I do the line structure, I mean, I do it upside down, then in my line structure, the net dipole moment must be going towards the fluorine like this. Okay, it cannot go towards this fluorine. It cannot go towards this fluorine because it would be discriminating. We shouldn't do that. That's bad. Okay, so it must be in between. That's why we place the net dipole moment in between our two main bond dipole moments. Does it make sense?
Yeah.
Yeah. So there's a net dipole moment in this molecule. What about the trans one? I want to talk to somebody. Can you give the microphone to what's your name, sir? Yes. Yes. What's your name, sir? Thank you for volunteering. I appreciate that. Yeah. What's your name, sir?
Andrew.
Andrew. Leo volunteered. You okay? All right. No need, it was me. So Andrew, what do you think about trans isomer?
I'm guessing it goes like horizontal.
Yeah. Let's draw them. Okay. Here's a bond dipole moment of the carbon fluorine going in this direction. Here's another CF bond dipole moment going in the opposite direction, which is equal in magnitude. What can you tell me? They are equal in magnitude, but opposite in direction. What can you tell me? When you add them up, will it be greater than 0 or 0? They are
Zero.
equal in magnitude, opposite in direction.
I believe it's 0, correct?
It's 0.
Yes. Okay.
Yeah, so they are equal in magnitude, opposite in direction. When you add them up, they're going to add up to 0. Yeah, and again, if you want to deal with the carbon hydrogen, same thing. You have a small dipole moment going towards carbon like that. Again, these are equal in magnitude but opposite in direction. When you add them up, what can you tell me?
It'd be the same.
It's 0 again.
Yes.
Right? So the dipole moments cancel out. Therefore, the net dipole moment for this molecule is
0.
0. There you go. So that's our non-polar molecule. Yeah? So net dipole moment is 0. Therefore, it's going to be a non-polar molecule. Now, last one. Remember your name, sir, one more time?
Andrew.
Andrew, can you pick a volunteer for me?
Yeah.
Everybody wants to volunteer, I know. You can pick anybody.
What?
It's Tyler? Tyler, right? Tyler, Tyler, thank you for volunteering, Tyler. Tyler, what do you think about this molecule over here? Is it polar or non-polar?
I think it's polar.
Okay, so let's draw the bond dipole moments and see whether you're correct or not, okay? So here's the carbon-fluorine bond dipole moments going in this way. Here's the hydrogen-carbon bond dipole moments, if you want to entertain them. Yeah, I mean, I wouldn't, but you know, they're kind of negligible. But what can you tell me about the net dipole moment of this molecule then, Tyler?
It's going to be going to the right, straight right, horizontally.
Yeah, going towards the fluorine atoms, right? So in between the fluorine atoms like this. So this should be the net dipole moment of this molecule. If I drew it on my line structure, it should look like that. Yeah? Wonderful. Thank you. That's it. And that's how we figure out the net dipole moment. We don't have to worry too much about, you know, the head to tail. So if you see all my bond dipole moments are, you know, like facing a certain direction, then our net dipole moment is going that way. All right, that will come with practice. Even if you drew the head to tail method, you will end up with the same result. All right. What questions, concerns, comments do we have? Now, we have talked about like several ways of determining the net dipole moment. We talked about the head to tail method. We talked about the symmetry. We talked about, you know, just by looking at the molecule where all the bond dipole moments are facing and how we can use that to determine the net dipole moment direction. Yeah. So you can choose your poison. No. All right. What questions, concerns, comments do we have? Anything that I can try to clarify? Okay. All right. Now that we know which one of these are polar, I want you to deal with the line structures now, okay? Because you know that they're easy to draw. So let's pick one of these polar isomers. I want you to pick, let's say cis isomer. Let's pick the cis polar isomer. Can you show me how two of these cis isomers do the line structure? I mean, it's easy, okay? Would interact with each other. Go ahead. If that makes sense, yeah. No. You draw a dipole randomly. Okay. So here's a dipole. Okay, here's the head, here's the tail. Now, what is the partial charge of the head of the dipole? That please, one more time. I need your help here. The arrowhead has what partial charge? Negative. Thank you. So we have the partial negative. Okay, and then the tail is positive. Okay, so when it interacts with another dipole, will it interact like this, or will it interact like this? What is more probable? So let me indicate charges one more time. This is negative. This is negative. Positive. Positive. This is positive. This is negative. What is more likely? A or B? Everybody, what is more likely? A, okay, let's take a vote. Okay, who says B is more likely? Who says A is more likely? Why is A more likely? I want to hear from like far away from there. A galaxy far, far, far away. Pedro, can you go all the way back? I mean, I want to try to include. Yeah, pick somebody from there. I guess anybody. They all want to volunteer. Perfect. Thank you. What's your name, Miss?
Elise.
Elise. Elise. Why is A more likely?
I think A is more likely because positive and negative would go together because like the attractive forces
Exactly.
and the other would repel.
Yeah, opposite charges are attracted to each other, right? On the other hand, when you have a situation like B, they're going to repel each other because the same charges repel, opposite charges attract, okay? So A is more likely. Now, how do we use that information to show how these two molecules would interact with each other? I know that the dipole moment, if I drew the molecule, the dipole moment would align on this molecule like this. Here's one. And then here's my second, second molecule that is interacting with. There you go. This is how these molecules are more likely to interact with each other because opposite charges attract. Yeah. All right. What questions, concerns, comments do we have at this point? Now, we just drew our first type of intermolecular forces. We are officially in Unit 3, Module 1. Of course, I use a segue, but that's okay, right? This is Unit 3, Module 1. This is the first type of intermolecular forces we learned. Now we get to name it. We have two dipoles interacting with each other. A dipole is interacting with another dipole. Dipole, dipole. What can we call it? Does anybody have any idea? Dipole interacts with another dipole. Dipole, dipole. What can we call it? What does that mean? No. What can we call it? Isaac, do you know?
Dipole
Thank you.
interaction.
These are group forces. All right. This is what we call dipole forces. Of course, this is one of the three intermolecular forces we are going to be talking about in Unit 3, Module 1. Now, what I'm going to do is this. I'm going to do this in the newspaper style. You know what do we mean by newspaper style? Okay. They give you the, like, you know, the most attractive part of the story, the entire story at the beginning, and then the details later. Right? Okay. So now I will summarize entire Unit 3, Module 1 right now. And then spend 3 lecture sessions talking about the details. Okay, it goes like this. Intermolecular forces, let's call it IMFs. Okay, are of three types. We have dispersion forces. We're going to talk about this today. We have dipole forces. We were introduced to this today. And then we have 1, 2. Right? Hydrogen bonding forces. So these are the 3 types of intermolecular forces. Okay. So when Jordan said that may the force be with you, they're talking about the intermolecular forces. Okay. So anyway, now these are the intermolecular forces that we'll be discussing in this module. I'm trying to organize your notes for you. And the dispersion forces depends on what we call the polarizability, which we're going to learn today. Oh my goodness, my eye. Polarizability. Okay. Higher the polarizability, stronger the dispersion forces. And the dipole forces depend on the molecular polarity or the net dipole moment. What should I use? Molecular polarity or net dipole moment? Should I use net? Molecular polarity? Okay. So it depends on the molecular polarity. So the thing to keep in mind is when I say net dipole moment, I'm still referring to the molecular polarity. Okay. So idea is greater the molecular polarity, stronger the dipole forces. And then the hydrogen bonding forces strength depends on the number of hydrogen bonding sites. Okay. This is a summary of Unit 3 Module 1, like 90% of the Unit 3 Module 1, like just half a page. Okay. So, any questions, concerns, comments at this point? Okay. So, we're going to come back to this. We're not done with this yet. Okay. We're going to come back to this and then we're going to add a little bit more details. So, just to make this more complete. Okay. Now, this is going to be the overview. Now, I want to mention one other thing before I move forward. So we talked about this. We saw how opposite partial charges are attracted to each other. In fact, the intermolecular forces are all about partial charges. Okay, so I'm going to write this. Where should I write it? Okay, maybe over here. Okay, so everybody should write this. Intermolecular forces, IMFs, intermolecular forces are due to attractive interactions between opposite partial charges. Meaning, if you don't have opposite partial charges, you don't have intermolecular forces. Okay? For you to have intermolecular forces, you have to have partial charges, and then the opposite partial charges of adjacent molecules are attracted to each other, and that is what we call as intermolecular forces. Any questions, concerns, comments at this point? Okay. Yes, Laila. What is that?
What about full charges?
Like ionic compounds? We'll get to ionic compounds later. So Lila's question is, what about like complete charges, like positive ions and negative ions and stuff like that? That we're going to discuss in ionic compounds. Now, intermolecular forces are between molecular compounds, not ionic compounds. And molecular compounds are made of only non-metallic elements. Is that enough for now, Laila? We're going to get to that, I promise. Yeah? But in Unit 3, Module 3. Okay. Now, let's do this. We got this done. I hope that everybody made this note very clearly. I'm organizing your notes for you. By the way, this is my favorite area in Chem 51. So let's have some fun with this. Now, just to summarize what we have discussed so far, we know the composition of the particles or the chemical formula, okay, which gives us limited information. Now, with this, we can determine the structure of the molecule. We drew Lewis structures, and then we know how atoms are bonded to each other. And then in Unit 2, Module 4, we talked about how the electrons are distributed or the charges are distributed within the molecule. In other words, the polarity of the molecule. We learned how to do that in Unit 2, Module 4. Now we know when we have like partial charges, like for an example, if you have red, that means partial negative. If you have blue, that means partial positive, right? And we know if we have partial charges like that, they can interact with each other. They are attracted to each other. And these attractions are known as intermolecular forces. Okay? And that is what is being discussed in Unit 3, Module 1. Entirely in intermolecular, it's about intermolecular forces. Okay. And then in the previous life, we have seen that these intermolecular forces determine properties such as boiling points, melting point, vapor pressure, solubility, and values like that. Okay. So what I want you to do is I want you to remind yourself about how intermolecular force strength affect the values of these properties. Go ahead on top hat.
I'm curious. Have you guys talked about like your cards sometimes? Yeah. Okay, that makes good. What about why that is? Right, so it's gonna be more. Right. The other side is reading a great difference. Density viscosity. Viscosity has to yeah, like, so I would just, yeah. I think it'd be a little out.
I think there should be enough time for that. All right. I'm going to close this discussion in 5, 4, 3, 2, and 1. By the way, just to remind ourselves, I think in a previous life, hey, it's nice. We did something like this. We can remember, okay? Stronger the intermolecular forces, higher the boiling point, higher the melting point, higher the condensation point, higher the sublimation point, higher the density, higher the viscosity, but lower the vapor pressure, lower the volatility. Unit 1 from Unit 1. I know it's been a while, but the question is asking the same thing. It's not anything new, which is just reminding us about what we have done before. And then when I walked around, some of you did not mention density. Density is also affected by the intermolecular forces. Stronger the intermolecular forces, more closely the particles tend to pack. As a result of that, you're going to have a higher mass in the given volume, same volume. Therefore, the density increases as well. Okay, so that's the idea there. If you did not pick density for some reason, I know that there are quite a few people who have that question about the density. Okay. Now with that, okay. Okay. I'll reopen the question. But do we have any questions, concerns, comments at this point? Okay. All right. Now we know these properties have to do with intermolecular forces. Okay. And then we know the intermolecular forces has to do with the partial charges. All right. Oh, Ronaldo is back. Hi, Ronaldo. You missed the first part. Okay. Now here's the question for you. You can use AI if you want to do this. Okay. Can you let me know out of oxygen, O2 and N2, which one has a higher boiling point? O2 or N2? I don't have. Okay. I mean, I want you to tell me which one has a higher boiling point. You can check. By the way, in my class, feel free to use AI all you want. Okay, but it's totally fine. I mean, you use that to understand the concepts. It's totally fine. Leo, which one has high boiling point? Thank you. So, okay, I was told that O2 has a higher boiling point. Meaning, O2 has strong intermolecular forces or weak intermolecular forces? Thank you. Now, everybody understand that O2 has strong intermolecular forces compared to N2. Now, here's what I want you to do. I want you to show me or draw the intermolecular forces between two O2 molecules. Go ahead. Where are the intermolecular forces? Can you show me? By the way, O2, N2, are they polar or non-polar? Non-polar, thank you. There's no electronegativity difference at all, right? Those are non-polar molecules. All right, go ahead. All right. All right. How many of you have an issue with what I just asked you? Because we discussed, let's see, I need my mask. I don't know, somehow. Okay, so it's okay, that's okay. All right. So we discussed how intermolecular forces depend on partial charges. And then we also know O2 is a non-polar molecule. Question. Where are the partial charges in a non-polar molecule? Do they have partial charges? No. So what's going on here? But still, they have strong intermolecular forces. They have intermolecular forces to begin with. Where are those? What are those? Let's answer that. Okay. So, we have a question. Lila, you're going to say something. Go ahead, please.
I'm just gonna say, is it because O2 can get closer to each other's
But where are the intermolecular forces or the partial charges that that we need to have intermolecular forces?
Okay.
Right? Okay. Now I'm going to solve that problem once and for all. Okay. So let's think about. Oh. Okay. Beyond that. Okay. Let's think about a totally innocent atom like neon or argon or something like that. Okay. Okay. With just it's one atom. There's no, polar bonds. There's no bonds to begin with, nothing. Okay. With a totally spherical electron cloud like that. Okay. Now, it doesn't have any partial charges. However, now pay attention very closely now, please. I mean, if you have your phone, I know that you tend to, look at your phone. Please put that away for a second just to understand this. And then you can take your phone back on and do whatever you want. Okay. Now let's look at this. Now we have a spherical electron cloud, meaning there are no partial charges. But when I introduce an external charge nearby, let's say a positive charge. what happened to this electron cloud? Yeah, electron cloud shifted towards the positive charge. As a result of that, now you have an area with a higher electron density. So this area has a higher electron density, meaning it's going to have a partial negative charge because higher electron density. On the other hand, other side is going to have, it's almost the nucleus is exposed. Nucleus is positively charged, right? Okay. So this area is lacking electrons as a result of that. Therefore, this area is going to get a partial positive charge. Now, what I did was I induced partial charges on a totally innocent atom. It was minding its own business. Just by bringing another charge nearby, I was able to induce partial charges. Okay. Now, this ability to have induced partial charges is known as, get this, polarizability. Okay. The ability to have induced partial charges is known as polarizability, and anything with electrons can be polar, non-polar, diatomic, monoatomic, multiatomic. It could be a hair, chair, anything that you can think of. If they have electrons, they are polarizable. Okay, anything is polarizable. Why? They have electrons. Okay. All right, one more time. What is polarizability? The ability to have induced partial charges. Okay. So when we have induced partial charges like this, we say that we have an induced dipole. We have an induced dipole. Okay. I hope that you made some sort of a note. Okay. About, yes, sir, Leo.
Did you say anything that has electrons?
Anything that has electrons is polarizable. I said that, yes. Yes. You have a question? Did I hear a question? I'm sorry. Okay. All right. Now, here's the thing. It's not just the like, external positive charges or negative charges that can induce partial charges on other molecules. Okay. So if you have a molecule or a particle, and just by bringing another particle nearby, you can induce partial charges on it. Why? When you bring another particle closer to another particle, that particle is going to have electrons as well. The electron cloud of the other particle can, here's a beautiful word, can perturb the electron cloud of the second particle. As a result of that, it's going to have induced partial charges. I'll repeat that. I mean, I know I have to repeat that like multiple times. I know that. Okay. So what I said was this. So we don't have to have an exact charge to induce partial charges. We know if you just bring another particle, they have their own electron cloud as well, right? That electron cloud is negatively charged. Just by bringing that electron cloud, that particle with the electron cloud near to this particle, you can perturb or disturb its electron cloud to induce partial charges on it. Okay, so this is what is going on in oxygen, right? When you bring another oxygen molecule near to another molecule, when you bring two oxygen molecules together, okay, they can perturb or disturb. That same thing. Perturb is a nice word because in quantum chemistry you will learn things like perturbation theory and stuff like that. This is what is meant. It's just disturbing. Okay, so the electrons cloud can be perturbed by each other. Okay, just by bringing another particle closer to each other, closer to it, the electrons cloud can be perturbed, and as a result of that, you can induce partial charges on these molecules. And these induced partial charges can interact with each other. Now, how do we draw that? I mean, I'll draw that and then I'll take your questions if you have any. So here's what I would do. I would go to oxygen molecule. Let me take a new page. Okay. Here's one of my oxygen molecule. Okay. And here's this electron cloud. Okay. And here's another oxygen molecule, and here's its electron cloud. Okay, when these two oxygen molecules come closer to each other, they can disturb each other's electron cloud, or they can perturb could be negative, this could be positive. Now, once you have induced partial charges, they can be attracted to each other, and that gives rise to a type of intermolecular forces called, does anybody know? What do we call this type of intermolecular forces? Yeah, I heard that. But before we come to that, let's call it this. These are known as induced dipole forces. Why? We have forces between induced dipoles. Okay. These are also known as van der Waals forces. Okay. Or London dispersion forces. Let's call it London forces. Okay. So in our class, we will refer to this as, let me use red, dispersion forces. Okay. This is the idea of dispersion forces. Okay. All right. I mentioned the other ones because I don't know. I mean, if you take MCAT or something like that, they might use terms like van der Waals or London or induced dipole forces. That's why I mentioned those. But in Chem 151, we will refer to this as dispersion forces. Okay. All right. What questions, concerns, comments do we have at this moment? Any questions, concerns, comments? Eden, anything? Yeah. Alana, you doing okay?
Right.
All right. You have a question? Thank you, Peter. Tyler, what's up?
Okay, so I'm gonna try to see if I'm understanding this.
Yeah.
So the oxygen it has induced partial charges, an induced dipole because it's near the other O2,
Yes.
which has partial charges. Well, where does that one have?
So no, give me a second. So they did not have partial charges to begin with.
Mhm.
When they come closer to each other, that induces partial charges on them, and the opposite partial charges are attracted to each other, and that's what gave rise to dispersion forces.
Okay.
Yeah. So this happens to us sometimes. Like with some, I mean, I don't know. When I was a grad student, I was sitting at a bus station, right? And I was minding my own business, and just somebody came to me, and that perturbed me. Okay, and that made me say hi to them. So perturbations doesn't have to be always negative, right? They can be positive as well. Okay, I wasn't interacting with that person, but just because that person came near to me, we started talking. That happens to us, right? Yeah, things like that happen to molecules as well. Just by getting another molecule closer to another molecule, they can start talking. They can induce partial charges on them, and they can start interacting. Yeah, that's what happened in dispersion forces. Huh? All right, what other questions, concerns, comments do we have at this moment? Okay, all right, let's have some fun with this now, okay? So we understand dispersion forces. Let's just go back to, okay, let's go back to our slideshow. Now, here are two particles. Can you tell me which particle is more polarizable? Go ahead.
That means you have to go okay, so yeah. No,
It's not, there are no trick questions. All right. I'm going to close this question in 5, 4, 3, 2, and 1. Okay. And here, this is beautiful. I like it. Okay. Most of us selected option 2, or particle 2 being more polarizable, and that's the correct answer as well. Why did you pick 2? Anybody? Why? Remember name someone, Anthony?
No,
What-
Caden.
Was it
Caden.
Cadence?
Yeah.
Cadence, go ahead.
Because number 2 has more electrons.
Exactly, that is it, right? Okay, the particle. So now, please get this. Particle 2 has more electrons and it is larger. As a result of that, it has a higher probability or higher chances of getting perturbed. And that is polarizability, right? Because more electrons, more volume means you have a greater chance of getting polarized or getting perturbed. That's it. That's why particle 2 is more polarizable. Okay. So to summarize that, that's an important thing that we need to know. Larger the number of polarizability is greater with more electrons over a larger volume. Okay. Greater the size, greater the number of electrons, greater the polarizability. Okay. So just to complete our notes here, we can go back to our chart. We can say polarizability depends on the number of electrons and the size. Okay. Greater the number of electrons, greater the size, high the polarizability, stronger the dispersion forces. Okay. So high the polarizability, greater the polarizability, stronger the dispersion forces. That's the relationship that we need to keep in mind. Okay. Now we know what polarizability depends on. Polarizability depends on the number of electrons and the size. Now keeping that in mind, let's see if we know how to count electrons. So here are 3 molecules. Let's see. Can you count the electrons in there?
Yeah. Yeah. Absolutely.
All right. I'm going to close this question in 5, 4, 3, 2, and 1. Okay. And here's the most popular answer. CF4 has the least number of electrons and CBr4 has the highest. And that's the correct answer as well. However, it is important that you know how we get that number 42 for CF4 and number 74 for CCl4 and so forth. Okay. So I'm going to show you just once so that you know where these numbers are coming from. Carbon atomic number is 6. That means it has in total, not just the valence, in total, it has 6 electrons. Okay. Plus, we have 4 fluorine atoms. The fluorine atomic number is, does anybody know? 9. That's 9. Okay. Atomic number of fluorine is 9, meaning it has 9 electrons in total. In total, not just the valence. Valence wise, it only has 7, but in total, it has 9. So 4 times 9 is 36. 36 plus 6 is, guess what? 42. That's how we get 42 electrons there. I'll do one more just to make sure. Carbon has 6 electrons. And then we have 4 chlorine atoms. Chlorine atomic number is 17. Okay, so each chlorine brings us 17 electrons, meaning we have 4 times 17, which is 40, 28, 68, right? 68 electrons from the chlorines. 68 plus 6 is 74. And that's how we get 74 electrons in CCl. Okay, so you need to be able to count the electrons, total electrons, not just the valence. That's the point there. Any questions at this point? All right, now the next question I already opened. I think some of you already answered it. So polarizability. Can you answer that question too? Which one is most polarizable? Oh, yeah, arrange them from least polarizable to most polarizable. Oh, this is great. Yeah.
You guys doing okay? You guys doing okay? It's one hundred miles from the road. It's also, It's like a part of
I'm not. All right, I'm going to close this question now. Okay. And we know high the number of electrons, high the polarizability. So here are our responses. Most of us said this, and that's the correct answer as well. CF4 is least polarizable. It has the least number of electrons, and it is the smallest molecule over here. And the CBr4, on the other hand, has the highest number of electrons and it is the largest, therefore it's going to be the most polarizable. Okay. And the connection to dispersion forces, we already discussed this. Dispersion force strength depends on the polarizability. Let me show you an example, okay? So if you have a smaller molecule, it is going to be less polarizable, and then you have less partial charges induced. Therefore, less interactions. But if you have a larger molecule, you have a greater chances of being polarized. Therefore, you have more partial charges to interact with. As a result of that, you're going to have stronger dispersion forces. And that's why with polarizability, the dispersion force strength increases. Okay. And we indicated that in our notes here as well. Okay. Greater the polarizability, stronger the dispersion forces. Now, keeping that in mind, can we try these last two questions for today? I'm going to open this. Oh, I can go there. Okay. And then I'll do this one as well. This has to do with the same thing. Let's try this first. By the way, I swapped neon argon unintentionally, of course. Okay, but that's okay. We can still run with argon in the last question.
Second question.
There are two questions. Let's do the first question I opened and then the last one. All right, this question is done. Let me discuss this really quickly, and then we can talk about the other one. I'm going to close. Yeah, the question is closed already. Let's see. All right. So please pay attention for like 30 more seconds. Most of us picked this as the answer, and that's the correct answer as well, almost 90%. Again, CF4 is the least polarizable. Therefore, it's going to have the weakest dispersion forces. CBr4 is the most polarizable. Therefore, it's going to have the strongest dispersion forces. That's it. Now, moving on to the last question. All of these molecules are polar or non-polar? Polar or non-polar? Non-polar, right? So helium, neon, those are noble gases. Yeah, definitely non-polar. CH4 and C2H6, they are hydrocarbons. We know for all intents and purposes, hydrocarbons are considered non-polar. So if it is non-polar, you don't have a permanent dipole. Therefore, there are no dipole-dipole interactions. We haven't talked about hydrogen bonding. There's no discussion about hydrogen bonding. Only possible intermolecular forces are dispersion forces. Okay. Keeping that in mind, can you tackle this problem? I'll give you one more minute. Make this is 3:30 now. That's okay. I swapped neon with argon, but that's okay. And argon is comparable with C2H6. All right. We have 1 more minute. So I'm going to close this question for now because we're running out of time. Okay. I'm going to close this in 5, 4, 3, 2, and 1. All right. And here's the most popular answer, and that is the correct answer as well. Let me tell you why. I'm going to discuss this, okay? So let's count electrons. Helium atomic number is 2, therefore it has 2 electrons. CH4 has 10 electrons. Carbon is 6. Hydrogen is 1. 4 times 1 plus 6 is 10. And argon is atomic number 18, therefore 18 electrons. And then C2H6, from carbon, we're going to get 12 electrons from 6 each. And then the 6 electrons from the hydrogen. So 12 plus 6 is 18 again. Now, based on the number of electrons, we know helium is the least polarizable, therefore the weakest dispersion forces, and then CH4 and then argon. But between argon and C2H6, argon is more, C2H6 is more polarizable. Why? It's a larger molecule because we have 2 carbon bonded to each other, and then we have hydrogens in there. Okay, it looks like this. While argon is just a spherical atom, okay, which is smaller than C2H6. Because C2H6 is larger than argon, it is more polarizable. Therefore, it should have stronger dispersion forces than argon, and that's why we pick this order for the boiling points. Laila.
Whole molecule, you think the single molecule would be larger?
Give me single atom.
Yeah,
Yeah.
even if the single atom is stronger, atoms in the molecule.
Yeah, usually, otherwise you cannot compare. If they have the same number of electrons, okay, then there will be a clear winner for the size of the particle. Yes. All right. So with that, have fun tomorrow with exam 3A. I think this is an exam 3A. And I'll see you next week to have some more fun with this. Bye, everybody. Yeah, and happy health.